Question 6, show that the unit for G, the universal gravitational constant, can be expressed as meters cubed seconds to the -2 kilograms to the -1. So as always, when we're doing this, we start with equations. We know F is minus G m1 m2 over r squared. We could immediately rearrange this to get G. The minus sign doesn't matter too much, so I mean, we could just get rid of it because we're just looking at the units. F r squared over, and again, we could put m1, m2, but we know that it's just their units that we're interested in, so I'm just going to write it as m squared immediately. R is already in meters, m is already in kilograms, so they're already in their SI units. It's the Newton that we need to sort out, sorry, the force part that we need to sort out. So as always, any equation you can think of to do with force allows us to define the unit within it. So a useful one to use is force is mass times acceleration. That's of course partly because I know that these have very simple units. So I can write down that in terms of units, if I use the Newton is equivalent to the kilogram meter per second squared. So I'm just using the square brackets to indicate that these are units I'm dealing with now. I've also changed color. So over here, G in units. So the units of G, I'm going to say are, so in here, I've got the F on top. So I've got a kilogram, a meter, and a seconds to the -2. Then I've got the r squared, so that gives me meters to the 2. And then underneath, this m is for mass, not for meters, of course. So that's got me a kilogram to the -2. And then I just need to gather them together. So in terms of meters, I've got a meters here and a meters squared here. So this gives me my meters cubed I was looking for. The seconds, I've only got one, so seconds to the -2, and then I've got a kilograms and a kilograms to the -2, so that gives me my kilograms to the -1. So the units of G can be expressed as meters cubed, seconds to the -2, kilograms to the -1.